This is the Math Map Book Club, where ordinary parents encourage one another to develop an extraordinary appreciation of math. We love what we know and struggle over the unfamiliar. Through weekly conversation and exploration among friends, we can begin to enjoy ideas that seem difficult. Join our book club as we discover how math helps us to know God and to make Him known.
Hello and welcome everybody to our lesson 17 Intersected Shapes episode of our book club. It is November the 19th. This is our last meeting before Thanksgiving. We're assuming that next week people would rather be baking cookies or peeling potatoes or doing something to get ready for however your family celebrates Thanksgiving. So we will meet today for lesson 17, and then in December we will be back and we will be doing sort of a Q&A style for 3 weeks, and then back to lesson 18 in January. So we're almost through 2D. We're going to straddle 2D over the holidays with lesson 17 today. So as we think about flashcards, as we're going through this list of strategies again, the strategy that was next on the list was to celebrate. And it made me think about what I was studying, one of the things that I was studying for my doctoral degree, which was math self-efficacy. And it's different to confidence because when we think about confidence, it's a general feeling, it's a general sense about ourselves, whereas self-efficacy is more specific, and it's usually more task specific. So you could say that I have a great deal of self-efficacy with arithmetic and not a great deal of self-efficacy when it comes to algebra. But I do have a great deal of self-efficacy that I can use the classical method in order to learn algebra. So it tends to be more specific. And one of the things that makes it valuable for us to understand is that there are specific ways that we can actually help to improve or build our self-efficacy. The most effective way to build self-efficacy is through mastery experiences. And that's one of the reasons why I think Lee has set the curriculum up in the way that she has, so that there's those small jumps in between lessons, and then there may be a bigger jump. But feeling like you've had some success is something that's going to build your self-efficacy. So if you got through, kind of got through complex, and now you're in monomials, and your student's going, oh, this is easy. I've done this before. I've got it. That sense of success, that sense of feeling like you know what you're doing, is going to build your student's self-efficacy. And even when they next year maybe look at binomials and it's a bigger jump or maybe more of a challenge to them, they're going to have that higher self-efficacy that's going to encourage them to push on and to believe that they can do that. So with our flashcards, that's why it's so important to include flashcards that our students can get, that when we include things that they know, they go, oh, I've got this. I'm feeling good about this. And so when they encounter the ones that are a struggle, they have that confidence in themselves or that self-efficacy to believe that they can master those hard cards too. We can also build our self-efficacy. It's called vicarious learning, which basically means seeing somebody else be successful or seeing somebody else do that. And we've talked about this before, about how we as adults don't always enjoy flashcards and we don't always enjoy memorization. But if our students watch us as role models, being learners and being successful, that actually is going to build their math self-efficacy. And so there's an opportunity for us there as teachers to really model for them what it means to learn our grammar through repetition and practice, and that does lead to success, and that will in turn help them to build that self-efficacy. And then the last thing that we can talk about is the idea of verbal persuasion. which means that when they hear encouraging talk, whether that's external or internal, that's another way to help build that math self-efficacy. So when you encourage your students, not just with great job, but wow, I'm really proud of you that you persevered and continued practicing those flashcards, or wow, look at how well you did in reading those flashcards, right? That when you give them that specific encouragement, that will help build that self-efficacy. And then also encouraging them with that internal talk to be positive, right? So we know that that has a great ability to influence our students. If they're thinking, well, I'm stupid, I can't learn this, that's going to take away from their self-efficacy. But if we can help them to build that positive internal talk where they're like, okay, I I can do this. I've memorized cards before. I can do this. Then we're going to help build that self-efficacy. And not only are we going to see that we're doing that with the flashcards, having confidence in the flashcards, but that type of self-efficacy is likely to transfer over to the lesson pages and to whatever else we're doing in our math education. So I just thought I would talk about that because we tend to talk about confidence more, which is a general sense, and a little bit harder to build up one's self-confidence. But because self-efficacy is so specific, there are ways that we can actually help our students to improve that and then see how that will in turn transfer to other skills. Any questions about flashcards or self-efficacy? You're muted again, Babs.
I'm not muted. I don't know why it's doing that. Can you hear me now?
Yep.
Okay. I think it's my internet must be slow or something. But I love the last part about the positive talk. And it made me think about, I think we had a testimony from a parent who she was talking about being positive in the way she talked about the math map. And it just struck me because when we don't understand something, we might not use that positive talk. I guess that's a good way to say it. And so I think that's true. If we say, well, I don't like this, I don't know why they're doing it this way, our kids are hearing that and then they're not going to want to do it. So, and that's not just with math, but like any subject that's difficult or unfamiliar, I think using that verbal persuasion is a great tool, just something for us to think about as we're introducing things to our students.
That's a great point. All right, I just remembered that I had kind of a math funny to share with you, so remind me at the end. Looking at our covers, this is one of my favorite covers. I had the opportunity to go to the British Math Congress. No, it was the British Congress on Math Education in 1999. And the theme throughout the conference was looking at Kandinsky's work. And I'm not normally a modern art person, but I really enjoy Kandinsky's work. And so every time that I get to lesson 17, I'm always excited because I just really like it. It makes me happy. And those are great things to talk about with your students too, right? So when we talk, I'm going to talk about our skills of learning here, but it's okay to say to your students, all right, does this cover make you happy? Or what covers do you look forward to seeing? Is it because you like the cover? Is it because you like the content? Right? Those are some great general questions that you can ask your students. This week, we are looking at some specific ways that we can pull in our common topics. And I thought that one thing that we can do, especially in the second semester, if we're starting to see how things have been building, we may want to bring in some assessment kinds of questions. And so asking your students to define terms from previous lessons. So looking at this cover, for example, we've talked about intersected before. We've talked about shapes before. So what do those terms mean? What do you think they might mean together? You could also, related to that, is comparing lessons with similar titles. We've seen that we have lessons that are called intersected lines. How might that be similar to intersected shapes? We've seen closed shapes and open shapes. Those are more 3D, but we could still, right? What does this general term shapes mean, and how might intersected be different than open and closed? We're always can go back and look at those dimensional patterns. So you can even do that in context. So you could say, well, what could have been intersected in 0D? Right? Nothing. What could have been intersected in 1D? Well, what kinds of shapes did I have in 1D? What kinds of things might intersect? What did we talk about? Let's go back and look at those lessons, right? So even those sets don't have a geometric understanding. We talked about sets in 0D and we talked about intersections there. What did that mean? So going back and looking at lessons in different dimensions to build up to where we are. Again, as we're moving ahead in the year, looking back and saying, okay, well, are there some charts that we've looked at before that reviewing might help prepare us for the current lesson? We might want to take a look at the polygon lesson. We might want to take a look at that intersected lines lesson, right? Or is there something that's on those charts that might help us to be prepared to have the conversation this week? And then we can always ask about how the art might testify about the content of the lesson, right? Sometimes I think the art is a better testimony than other times. This week, I think it's a great testimony, right? What does it mean? If we look at our art, what does that suggest to you that intersected shapes might mean? Anybody have anything they'd like to share about the covers?
Can
Of
you
course,
hear me?
yep.
Okay. At this particular cover, I don't know why, but it always makes me think about cacophony, like when we studied it in music. And at this season of my life, I feel like my life is with this picture because we're getting ready to do Thanksgiving and Christmas and all the things. And it's like, and so I don't know. I always think this is a perfect like cover for this time of year because it feels like it's just I feel like there is a specific place for everything, but it looks like it's thrown together. So
I
could
like these.
also go ahead,
I
Jen.
like Kandinsky a lot also. And I wouldn't say that I'm well versed in modern art either, like you said earlier, but I really do like this cover a lot. And I think it goes back to what you were saying about how our lives can feel like a lot going on, but everything does have a place.
Even in the instance where we will be doing this, like in January, we're trying to recover from Thanksgiving and Christmas. And so this is kind of like my life too, even in January,
Right.
a cacophony.
I
well,
was
don't
thinking,
you go ahead.
well, I was thinking that exact same thing. As a mom with an A and B student, where will I be in January? I will be knee deep in science fair and mock trial and short stories. So I feel a little bit of this.
And I was going to say that I think the first time I saw this cover, I don't know that I was like thrilled about it necessarily, but it's come to be like an old friend. Like I recognize it and it's beautiful to me now. So maybe that's kind of the layering effect. And I don't know, like when you hear a song, sometimes your kids are like, oh, this is a great song, and you listen to it. You're not familiar with it, so you're just not like, that was whatever. But as you hear it more and more, you're like, oh yeah, that's really sort of that same thing. An old friend.
I like that, Jana. I'm not sure what it is about it that I like so much but I think it's the colors. Like there's sort of there's the soothing colors, even though you've got this jarringness to it, there's a soothing quality to it. But I love that idea that you're all talking about how our lives feel like a cacophony when we have all these intersecting, right? All of these things intersecting that, right? You've got the holidays and you've got, kids' performances and sports championships and extra special projects, and they're all intersecting, right? And then church has extra things. And so all of those things are intersecting, and sometimes those intersections are challenging, right? If they're all at the same time, what does that look like? So I think there's a lot of great conversations you could have with your older students as well as your younger students on this cover. Of course, every week we talk about where we are and the fact that we are here on lesson 17. We are almost to the end of our 2D lessons. That notice that is the biggest chunk of our year is 2 dimensions, that there's a lot of content in there. And so we're nearly through 2D. We're nearly there. And I think then our students are going to have that opportunity to start to see some of those dimensional patterns that are unfolding as we get to 3D and 4D. And so on day 1, going back to our different strategies for our lesson pages, and our strategy this week is that reminder to work with the multiple domains. One way that you can do that is as a parent, right? Not just when you sit down at the table with multiple ages of students or students that are working through different domains, but as a parent, remember that in the Math Map Companion, you can see all of the different domains up through and including binomials. So they're not all available for print, but you can see all of those different domains. So you could open up lesson 17 in naturals, in digits, in integers, in decimals, in reals, in monomials, and you can even see the preview of binomials. I mean, so you can go and take a look if you're trying to get a handle on a particular exercise or a particular section. You can go and look at all of those different domains in the companion. I think this is a great opportunity to remember that we can use our older students as resources and to use our younger students' domains as resources for those students. So they can review narrower domains if they're looking for hints to their lessons. And they could also encourage or tutor your younger students, right? That math self-efficacy that we just talked about, it could be you that's modeling for your students what it means to be a lead learner, but it can also be that that older student is going to model for your younger student, right? How do I do this? Oh, I found some success. And so seeing an older student go through that learning process is going to encourage the younger students. So I know that there's always this sort of tension between needing to sit perhaps with one student more than another, but there's a value in truly having our family math time together, at least a portion of that together, where our older students can model for our younger students. Or sometimes it's the younger students having a success and encouraging an older student. But that working together is a great opportunity that we have with the Math Map. And then you can certainly just work through the lesson pages together, right? So you could say, okay, we're going to work on this section and let's look at each other's booklets. What do you think? And actually work together on parts of the lesson pages, not just at the same table. Any questions or anything you'd like to share? So our day 1 lesson page here, lesson page 1, I think that there's a lot of review in this lesson because we're going back and we're reviewing areas and perimeters and names of shapes, names of functions. This is a great opportunity to think about it as a review lesson for what we've been doing. And 18 is going to sort of review some of those ideas in a similar way. So we really do end our time in the second dimension by looking at ways to integrate all of these different things that we've learned. Are there any questions on page 1? So on day 2, we practice our common topics of invention. This week, our common topic is testimony or authority. And I thought that I would share how I see this. So this may not be official CC. This is me talking about how I understand testimony and authority. That testimony is a witness, right? It's what is testifying to the truth of this. So we could ask our students, right? What might be a witness to the truth of concepts on this page? Well, a diagram might be a witness, right? Actually graphing something might be a visual witness to something. Or we might solve an equation, and that might be a witness to the truth of a solution. Then we can also look for real world examples of concepts. Right? So when we're talking about intersections, going outside and saying, okay, well, what are some things that are intersecting outside? What does it look like? Right? If I have 2 branches and they're straight branches, how can they intersect? Well, they can only intersect at one point. And we can go out and we can find examples of that and match it to the intersection of 2 lines, or find examples in the real world of parallel lines that don't intersect. Then the other thing we can think about is authority, which is that how do we know these concepts are true? Which is a little bit different to the idea of a witness, and that might relate to laws or properties. So what's the definition of parallel? And so how does that help us to know that parallel lines don't intersect? So those ideas may be getting a little bit more into the math understanding versus practicing testimony and authority, right? But I think especially the testimony, and if you're looking for real world examples with younger students, when you see some images, if you can find sort of the real world examples of those images, that's a great way to talk about testimony, right? Let's go and find this in nature, right? How does God's creation testify to these ideas? And that's something you could do with younger students without having to dig super deeply into the math concepts. Anybody have anything they'd like to share about testimony or authority or the common topics? Looking at page 2, we see that we're practicing our functions again. And so hopefully for your students, they're going to start to see the repetition, right, that we've seen these functions. We saw them in lesson 11. We saw lines in lessons 9 and 10. We saw the functions in lesson 11. We saw them again a little bit in lesson 13. We're seeing them now in lesson 17. So hopefully they're starting to see that these are a recurring theme in the math map and something that over time they're going to become familiar with. Any questions on any of the concepts here on page 2? So day 3, we're looking at our I cubed page where we practice our core habits of memoria and we consider arrangement. And this week we're talking about naming. And really, naming is using appropriate language. And sometimes in order to do that, we may have to look up unfamiliar words. So a great thing to do with our students on this page is just practice looking up unfamiliar words. How do we do that? Whether it's a math page or a page in a book that you're reading or a science resource, whatever it is, when we find an unfamiliar word, what do we do with it? I was really fortunate. I grew up in a home where we had this great big dictionary. I mean, I think it was this thick, and it was on a book stand, and it was in our living room. And anytime you asked, well, what does that word mean? You were sent to the dictionary to go and look it up. And I think that really developed in me this lifelong habit of not just skipping over words that I didn't know, but of taking the time to look them up and say, okay, well, what does this word mean? So this page is a really great opportunity to establish that habit with our students to say, well, let's go look that up. The glossary is a great resource. I was working on that this morning, so it's getting closer. We're making edits and we keep finding some words. Babs helped me find 3 more words to add to it this week. So we're getting closer to hopefully that being something that will be ready to print. I know that's been a most requested item, but it is available through the companion. So that's a great resource for looking up and getting a definition. But there's also lots of other dictionaries. One thing that we want to help our students to understand is that math words tend to be more precise than words in the general usage. So for example, the word line, it's really hard because we use it in 2 ways in the math map. We use it in a very general sense, like you would as a drawing, right? It's just a line, and it can be curved, it can be looped, it can be open, it can be closed, right? I'm going to draw a line. But it also has a very specific geometric meaning, which we would think of as a straight line, right? So when I talk about a line geometrically, I'm talking very specifically about the one single line that will go through any 2 given points. So when we talk about naming things with our students, appreciating the specificity of math terms, I think is a great thing to help our students to appreciate that we might use words in more than one way, but within math, they tend to be specific. That's also one of the things that can make it hard because there is a lot of nuance, right? So just today, as I said, I was working on the glossary and the difference between below the curve and under the curve. They sound like they should mean the same thing, but there's a nuance, there's a shade of difference between them because below the curve is physically, where am I? I'm below the curve, whereas under the curve is generally meaning anything between a function and the x-axis. So it actually could be above the curve, right, as well as below the curve. So there's shades of meaning, and that can make it challenging sometimes if we don't dig deep. And so we're not going to do that in 1 year, right? That's the course of many, many years of studying mathematics. We're going to start picking up on those nuances, but it starts here with our students by looking up those words and using the appropriate language. And then page 3, you see that we're continuing to look at some shapes. Here, I think, is one place where you're going to start to see students doing more what looks like algebra at young ages, right? Because we see these X's and Y's. So they're not actually doing anything in the algebra. Notice that they're copying. And so they're building up towards being able to understand what they're doing algebraically, right? Which we're just here introducing in monomials. So they're not even doing the full process in monomials. So we're building towards this, but we're building just that familiarity with algebraic notation through copy work. And then on our 4th day, we have our careful calculations and using this page as assessment, right? We talked last week how you could save it for review. We know that a lot of parents like to use this for assessing. And so you can do that and not just look for what was right or what was wrong or how fast did you do this, but asking your students or observing which of the exercises are the most challenging. Was it challenging because you didn't understand the content or because the computations were hard? And then how could we shore up those challenging areas? Do we need to spend more time on the flashcards? Do we need more computation practice, maybe with quick flip arithmetic? Or are there some chart or lesson pages that we could revisit? And so taking the time to not just correct the careful calculations page, but to determine, right, is this Why is this a challenge for our students? And then our page 4 has some different things going on. Lee chose to put in some age problems here, or some time problems on the 4 set as a way of looking at, right, so where do our lifelines sort of intersect, right, when we're thinking about how old different people are when they're together, and so forth. Any questions from page 4? So, of course, as always, we're here to support you. Babs is just, I like to just publicly, honor her as often as I can, because she works so hard to get questions answered and to be thorough and keep the errata up to date. So, I don't know. I just really appreciate her. And so I want everybody to know how amazing she is and what a resource you have in being able to email the math@classicalconversations.com and get help. She is there and she will help you directly or push you towards the right resource. So we don't want anybody to ever feel like they don't know how to get help, because she will make sure that you get the help that you need. And then just a reminder, we won't be here next week because hopefully you'll all be doing fun holiday things. So we had a couple of questions that have come in this week that we chose to put here. And so one of the questions that we got was the question about composite functions and how that works. And so the idea behind a composite function is really that you're using a function as an input instead of a number as an input. And so all of these are in terms of x. So that's one thing that we notice, is that all of our functions might be in terms of x, and then we say we're going to use that function as the input. When we're evaluating, generally we work from the inside out. You don't have to, because composition is associated, so I could work kind of from the outside in, but most commonly we think of being worked from the inside out. But one of the things to note is that composition is not commutative. So the cases here would actually happen to work out if we reverse the order, but that is not always true, right? So there's a mathematical sort of understanding, is that when we say the commutative law doesn't hold, it doesn't mean that it never happens, but it means there's at least one case in which it doesn't happen, right? So if you look here, we're not talking about the commutative and associative, but I just wanted to point that out, that as we look here, we're looking at these in different orders. So let's look at the left-hand side. We have f of x equals 6x, g of x equals 4x, and h of x equals 2x. And so if I substitute in 2x for h of x, right, well, that inside of g would be that 2x is going into the place of x. And so I would be 4 times 2x. And since I have f of g of h of x, if this part here is my g of h of x, that has to go in the place of the x in f of x. And so when I multiply that, I get 6 times 4 times 2, which is 48x. If we look at the second one, this time we have f of x is our inside function, so that would be our 6x. H is next. So that's 2 times x is going in the place of the x, so it becomes 2 times 6x. And then that whole expression is going in the place of the x here, so we get 4 times 2 times 6x, which again is 48x. And so if we continue that here, we see that we have our 4x. That's our g of x is inside. then our 6, and then our 2. And all of these equal 48x. And so it looks like the commutative law holds, but it happens to hold only because we're all looking at product functions. I'm just going to show you an example where it wouldn't hold is if I had f of x equals 6x, but g of x equals x plus 1. So here, if I said f of g of x, that was going in the place of x. So it becomes 6 times x plus 1, or 6x plus 6. But if I said f of g of x, notice that this time 6x goes in the place of this x, and I end up with 6x plus 1, which is not the same. So as long as there's one case where the commutative law doesn't hold, we say it doesn't hold for all of it.
Hey, Kirsty, it looks like those are exactly the same to me, the way you wrote them. Did you mean to do g of f of x in the second one, maybe?
Yes, I really did mean to do g of f of x.
Okay.
In my brain, I did do g of f of x.
Good.
Yes. In my brain, that was g of f of x. So thank you for pointing that out, because even when I looked at the screen, it wasn't until you said that that I saw that I had not written what I thought. So. And so on the other side, we'd see the same thing, right? That here h of x goes in first, then my g is the 3, and then my f is the 2x. If my f of x is the first, that would be my first, h would be my 4, g would be my 3, and then if g of x was my inside, right, then f is 2 times that, and h is 4 times that, and all of those would equal 24x. Any questions other than me writing things wrong?
I'm glad that I'm not the only one that does that. I'm just curious. So I'm looking at the bottom here where it says composition is associative, not commutative. So the associative part, I'm trying to remember what that means. So you could do like, you could
Well, if we go
start on
back
the
and look,
outside.
yeah.
And,
So here I could say, okay, I could do 2 times 3 is 6 times 4 is 24. Or I could do 4 times 2x is 8x, then times 3 is 24x.
So with your example over here with the 6x and the x plus 1.
Notice that my order has changed. So in this case,
Oh, right.
we can work through one. Let's look, because really you have to have 3 functions for the associative. So let's
Okay, gotcha. I understand. Yeah.
Okay.
Yeah.
Is that good, or would you like to work
Yeah,
through one?
I'm fine if other people
Okay.
are. When you said that you need 3 to make it, then I'm like, oh yeah, of course, because if you only have 2, there's only one order you can. Yeah, that makes sense.
Okay.
And the word composition, I'm trying to, so composite functions. It's read F is composed with G, composed with H, or like you were just saying, F of G of H. And so doing that is called composition. Compounding kind of, or
Yes. So if you think about that, a compound something is something that's been put together. A composite number is a product of 2 primes or more, 2 or more primes, right? So you're either prime or composite. Even if you think about, if I'm composing, if I'm writing a composition, right, I'm putting different pieces together. And so that idea of a composite function is that I'm taking different functions and I'm putting them together. The way that we do that is is making one the input of the others.
yeah, good.
And it's good to see this if students can grasp this idea I mean, it's helpful here, but it's also going to be helpful for those students who want to go on and really become masters of calculus, because we're going to see that we can take functions and we can multiply them, we can divide them, we can add them, but we can also compose them. And it's those composition of functions, if you can understand the pieces of those compositions, that are going to help us to calculate derivatives and integrals. So
I'm thinking
not,
about the word as a Latin derivative, like position is like putting, you know, and then calm together, right? So you're
yeah.
like putting them together. Yeah, very good.
And this is why, and this is also why we narrowed it down and we said, okay, and I always forget the number, right? I should know after all this time how many functions we have. But there's like 17 functions that we've identified, and there's really almost fewer than that, right? But we said we look at the sort of polynomial, the power functions, where you've got your polynomials, your rationals, your radicals, you've got your trig functions, your exponential functions. Those are your broad functions. All the other ones are going to be created from those. That's almost like your chart one, right? Where we have all the different pieces and then we put them together. That we have all these different functions, and I can, as I said, we could add them together. So I could have, right, just when we see x squared plus x, we're summing two different functions. Or I could understand that x times x plus 1, I'm multiplying two different functions. If I said x divided by x plus 1, right, now I'm dividing those functions. If I composed that, right, it gets lost when we're thinking about polynomials. But if you saw sine of x squared, that would be a composition of functions, right? Or sine squared x is a composition of functions because it's a composition of sine of x and x squared, right? And so I can compose it both ways, right? That's where we say it's not commutative because each one gives me a different thing. But that's how we have all of these different functions, right? That's how we create all of these different functions, is by taking those functions that we're becoming familiar with and looking at all of the different ways that we could put them together.
The building blocks, those are the building blocks.
Yes.
So the composition of functions, is there a name, like that's not calculus or trig, that's actually just advanced?
I would say that's your algebra. That's what you're,
Okay.
yeah.
And I noticed that circles and ellipses are always at the bottom of that chart, but those are not functions.
Correct.
Can they be, so can you compose with them?
That is a really interesting question. I bet you could. You'd get some weird, funky things if you did that.
Okay, I don't I don't need that kind of excitement in my life. Thank you.
So the only reason why I hesitate to say yes is that because you end up with those, right? You end up with a y squared and an x squared in almost all of those.
Right.
And so I can't say, oh, I mean, right, if y equals this, where do I substitute something in? So I would probably need to write it as a function first, like sort of like that half function where you sort of solve for y and take the square root, and so you get half of it, and then maybe compose it with something else, and then see what that would look like. But that would be a really interesting. I mean, if you think about it, like your circle is x squared plus y squared equals 1, or your r squared. And if we were to substitute sine and cosine, we know that sine squared of x plus cosine squared x equals 1. So there's kind of a relationship there, right? But you're now composing it three ways. Yeah, I'd have to kind of think about that and play around with that. But generally speaking, when we think about composition, we need to be able to write it as f of x, and those conic sections or those relations usually can't be written as f of x, right?
Because that's the same as y, and you're using y as
Yeah.
a yeah, that makes sense. Good.
Good question, though. So are there questions that you guys brought today or anything that you guys would like to talk about?
I
While
have a
we're giving
question.
everybody a minute. All right. Well, I was going to say, while we're waiting for the first person to be brave, I'll tell you that I thought this was really funny. So my son is eating his breakfast this morning before he left for work. And out of the blue, he goes, "So Mom, like, what's your favorite base?" And I'm thinking, I said, there's a lot of really cool stuff that happens in base 3. So I said, maybe base 3. That's really kind of like interesting. And he's like, he goes, okay, well, and so he sort of asked me a question about base 3, and he goes, would you want to know what my favorite is? And I was like, no, like, this is really great that we're having this conversation over breakfast. What's your favorite base? And he goes, it's base 0. There's no digits. There's no math. Okay. Okay. I will give you that one. So anyway, I thought that was kind of funny. Not
Spoken like a
quite the
true
in-depth
boy.
conversation I was expecting, but you know.
That is funny.
All right, Andy, what's your question?
So, looking at monomials, book 12, page 4, my daughter and I were talking about scale factors. And she was saying, like, to go from the small one to the big one, the scale factor would be 12. But the answer has it as like the smaller one divided by the larger one as
So
1/12. So, I mean, 1/12 is the same as, or is inverse of 12. Is that
yes. So I think at some point we're going to need to be better about telling people which scale factor that we want. Because of space, I think that what happened was that a lot of times Lee started off and wrote a problem where she gave people the order that she wanted, but then moved on to not telling people what the order was. And that's led to some confusion. I think in general, Lee tends to think right to left, right? That our scale factor, just see if I have my pen on. Yes. That the scale factor, if I have shape A and shape B, and we know that's not how we would actually name them, but she tends to think B to A. But they're both valid, right? We just need to know what was I thinking. So she tends to, let me erase look at Babs, right? Lee tends to think right to left. So she would look at this and go that this was 12 to 6, which is 2. She wasn't always consistent. So there were times where she might have said, gone the other way. But in all of these cases, since she's given you the scale factors, that's all that she's thinking is the right 6 to 3. In this case, she's just telling you that scale factor is 2. Here we could see, right, 8 to 8. But if we do it the reverse, as long as we understand that I'm either saying, if I did left to right, I'm essentially saying that K times my small one equals my big one. If I did right to left, I would be saying that my little one is some fraction of my big one. or vice versa, right? And so as long as our students are appropriately thinking through what that scale factor means, then I wouldn't worry if they end up with the inverse there. But Lee is trying to make it so it's always right to left, or that she specifies which way it is. So
Awesome. Thank you. Looking at this one, my daughter and I were working through checking them last week, and I was like, stop giving me that side angle side. And she just started laughing. She's like, I'm not giving you sass. I'm like, it can get kind of fun
that's
with
fun.
congruency. We were talking, I had to step in real quick, like for my challenge B director last week doing the math map. And we are talking about week 13, and the students were like, it's like label the vertices A, B, C, D. And so then we were talking about, where the chord and the tangent and all that other stuff. And I was like, well, it says like draw tangent AC, but I guess if you don't label it A, B, C, D, you're going to get something completely weird. And so we had a lot of fun with that. At least I did. The kids were like rolling eyes, but so then I was like, what would you label this then if you drew a line from A to C? Would that be secant, chord, tangent? Like, what are we doing? So that was fun.
Well, that's good. And you being excited is going to help them, even if they won't admit it.
Yes, the tutor came back. She had a doctor's appointment, and so whenever she came back, she asked the students how it went, and they're like, "It was a lot of fun." She's
Oh,
like, "How did you
good.
make math fun?" I was like, "I don't know. I was weird."
Yay. Are there any other questions?
I don't have a question, but I was just going to say that yesterday we had debates in challenge 3, and so it took the whole morning. We didn't have a whole lot of time for all of our other strands. So I showed them Desmos, and we looked at everybody that has the math map. We looked at your transformation, the chart in the transformations. So they would look for the shape they wanted, and we would plug in stuff, and then if we needed to dilate it to make the mark, then they would look at A has to be greater than 1, and it was so much fun. I don't know if it's really CC pedagogy or but it was an unusual thing, but it was definitely fun. Andy, like you're saying, making math fun.
That's great.
Yeah, I also told them about watching week 16 and how the really cool thing about tangents and circles, like that you explained to us last week, Kirsty, and they're just like, okay. I thought it was cool.
One day they'll be excited about it.
Yes, one day. I had one more, not like exactly a math question, but from fractions, book 13, page 2. I was working through that with my son today, and I noticed on the errata that it says that the M is not, what did it say? It was like that the notations of M are not uniform. So it made me wonder, is there a time and a place where M is used in talking about the circles and ellipses, whether a line is a secant AC, tangent AC, or chord M AC? And is there a time whenever you use, I assume the M means measure?
Yes. Without seeing it, I'm not sure how to answer. I don't know if Babs looks like she's working on pulling that up for us. Something must be going on in my backyard because my beagle is running from window to door. So while Babs is pulling that up, this may not have anything to do with it, but I will point out that when we have a circle and we look at an arc, right? So let's say arc AB. We can name arc AB. We can talk about the measure of arc AB, which is the same as the angle there. So this is going to be a degree measure. And we can also talk about the length of the arc, which is going to be a linear measure. And so this would be some number of degrees, right? This would be that number of degrees over 360 times 2 pi r. And so it'll be a fraction. So there's 3 different things that we can think about when we talk about arcs. Tangent line is missing. Notations are not uniform. Yeah, I don't know what those M's are there for. They shouldn't be. They should just be like.
Is that measure? Is the M there to say measure? Because
It
sometimes
is, but it doesn't really fit in this case. So I think that somehow it was supposed to be, they were supposed to just be written as segments or lines. So like BD should be written this way. AC should be written this way. For the chord, and the tangent would have been this way. So I think just somehow those notations got lost. DE looks like that's a tangent, so that would, yeah, so those, I don't know what those M's are there for, but they
Yeah, that
shouldn't
was
be.
that was my question. I
Yeah.
started thinking more deeply into. I thought measurement would be like an arc, right? It wouldn't be
Mhm.
a line.
Right.
Thank you.
Yeah. So does that help? You're welcome.
Yes.
Well, happy to answer any other questions. But if there aren't any, I just want to thank you all for being here. We're so thankful for all of you that come and join us and make it lots more interesting than just hearing me speak. And we thank those of you who are watching our recordings as well, because as long as we have people watching and attending, we will keep doing the book club. So please keep taking advantage of this resource. And enjoy Thanksgiving. I think it's one of our more mathematical holidays because we have all these pies, right? And so we can celebrate pie, and it's appropriate because we're doing circles. So you can talk about circles and central angles and arcs, right? So you could talk about with your, children, do you want to compare the length of the arc of your pie or the measure of the arc of your pie? And then there's those weird people who just like segments, and maybe they cut off, their pie, and so they don't have the full piece. So there's lots of things you could do where you have to eat pie in order to study your math this week. So enjoy that.
We'd get some serious eye rolls with that too. My father-in-law,
Yeah, probably.
right? My father-in-law likes to say pie aren't squared, pie are round.
There you go. That could be your family t-shirt.
He would love that.
Mhm. Well, you guys have a great holiday.
Thank
Thanks,
you.
you too.
We'll see you guys in a couple of weeks.